a number of similar results also. For example, suppose you want to calculate the Fourier transform of the characteristic function. Then you use exactly this and use some induction arguments on exteriors to give a calculation for the Fourier transform. Very pretty one. It doesn't, not quite as nice as you'd like, but in simple cases it works very well. Okay. Now, associated to this also is a partition. So C, first of all, it goes to a nice formula for this, and C goes to a partition of the Euclidean space. And what's the partition? Well, I take this, I just take the nearest point partition. So it's and so and I have to be a little bit careful about open and close, but basically that's the way it works. And so this gives me, every convex body gives me a partition. And if you look at it, you see there's some sort of relation between these two ideas, because here, for example, what we're looking at the characteristic function of this is equal to the characteristic function of this times some piece like this. And if you look in higher dimensions, what's going on is very similar to what we saw before, because what's going on in the transverse direction is an acute cone, and what's going on here is some kind of partition. So this is very strongly analogous to the partition of arithmetic quotients. In fact, there's more than an analogy. It's actually, in some cases, it's a direct relationship in the following sense. I won't say any more about it, but there's a notion of a building of a rational group attached to a reductive group, a split group. I mean, a semi-simple group, actually, is the best way to put it. And what's really going on here is that the partition here is a partition of something related to the building in some very weird way, which I don't understand quite entirely. Now, the building has the property that if I take any two simplices in the building, then they're contained in a Euclidean piece. And the truncation, the partition of the building, is exactly the partition on these Euclidean pieces in the building. It's some very strange thing. Okay. Okay. And now, I can tell you what Arthur's truncation property is. So yeah, I need some more notation. So ta hat f of C equals the characteristic function of the exterior of f with respect to C. And so what this is really saying, and this is this, so what this is saying is char C equals sum over f minus 1 codim of f of ta hat of f C. Just another way of rephrasing the same thing.
Fourier transform on the left. So now you took the Fourier transform.
No, there's no Fourier transform.
No.
No, there's no. It's just Arthur's notation. If I gave you any other notation, you'd look in Arthur and you'd get confused immediately. So so Arthur has, well, I'll explain. He has two tas, one with a hat and one without a hat. Okay.
What was the relation now between these two pictures? I didn't quite get it.
Between this and that, well,
Here's something.
there's a relation. I'm being rather vague, so I can give a name to the relation, but I'm not going to spell it out. The pieces here, the characteristic function of a piece associated to this face is the characteristic function of the face times the characteristic function of some cone transverse to the face. Okay? I don't have a... I've been a little less lazy. I could have drawn some 3D pictures, but you can sort of see that. I mean, if I take a point, and all the nearest points to that point form a polyhedral cone of some kind. So Arthur's truncation. So we have lambda, G, G, T, more or less the same notation as I have. We'll leave out the T again. Now, it's an extremely strange definition when it was first made. So Arthur wrote in 1983, and Verne, Ishida, and Briand wrote, I don't know, maybe 1995. Nonetheless, Arthur came up with this definition, which is exactly this definition made suitable for Arthur. So it's the sum over all P modulo gamma conjugacy of E PG of tau hat of P times the constant term of f of P. I'll explain what these mean. So f of P equals the constant term of f equals the intersection f and tau hat P equals the characteristic function on P of the inverse image of and EP equals sum gamma intersect P gamma of FP, EP of F, F of gamma G, where F on gamma intersect P divided by G. So this is basically an Eisenstein series. Now, it's a very strange definition for many reasons, but at least has one familiar property. Suppose that instead of the constant term here, I just took F. Okay, now in that case, what I'm doing here is just taking my function F and I'm just chopping it away. So these are all the exteriors. It turns out that by doing this, I'm looking at the exterior somehow. So this is essentially the same definition. So it's the analog. Oh, I'm stupid. I'm sorry. Somebody, I'm sorry. This is where I made my mistake. Tau P. And this is wrong too. I'm thinking ahead. We erase the hat. We make crits happy by not having a hat. I'll explain where the hat comes in just a moment. So this is not this cone. That's the important point. This is the other cone.
So is there a sign in the partition?
Yeah, there's a sign, yes. Co-rank of P. Okay. Yep. So there are a number of strange. So first of all, it's really stupid. So tau hat is the.
Tau hat is.
I'm sorry. This is tau hat. Yes, I'm just thinking very hard. This is Arthur's tau hat. Yes, that's right. Okay. Okay. Okay.
EPG again?
Who's?
The EPG.
It's a parabolic. It's the Eisenstein series. So I make it gamma invariant, in other words. And there are a number of miraculous things about this. So the first amazing fact is, so the property number one is that this sum is locally finite. Okay, now that's kind of intuitive and it's kind of not intuitive all at the same time. Why is it intuitive? Well, suppose instead of taking the constant term, I took f itself. So then what I'm doing is just chopping away the function on giant pieces. And if you look at what happens in the partition and you combine that with remarks I said about Euclidean partition, then if replacing fp by f, I get f restricted to the piece xp, well, gpp, gpg. So that's one thing. So that's one thing where the Euclidean truncation and Arthur's truncation they sort of fit together in some nice way, although there's something. But I'm not doing that. So if that were the case, then because of the partition, the sum is, again, it's obviously locally finite because of properties of the partition. But in this case, I'm just taking away this, and it's not so clear, and it's not too difficult, but it has to be proven that the sum is actually locally finite, which it is. So it can be defined, as Joseph says, on any measurable function.
For SL2, does this coincide? For SL2, does this coincide with
It coincides, that's exactly right. Sure, in that case, I'm just taking away the constant term above a certain point. Okay. Okay, and then it has the same properties, which I've now erased, but it has the same properties as I wrote before. But now, the properties are not so. So A, they're 0, 1, locally finite. 2, strong orthogonality. 3, support. 3, rapidly decreasing. At infinity, if f is A and G, uniform moderate growth, and 4, support on G implies OG F equals F. Okay. Now, but here the strong orthogonality is a little bit harder to prove. You can prove it by induction coming down from the top. Now, rapid decrease is actually, it takes some care, but it's not very difficult. It's explained in Harishchandra's notes on automorphic forms. Okay. I'll take a break. Are there any questions?
what is written in the last item?
Support on, if I have a function, it's the same condition as before. If I have a function with support on GG, the partition piece corresponding to G, then the truncation does nothing to it. Okay. Yes?
Is there anything with strong orthogonality along the way? So if you truncate more and more and more,
Yeah.
then all the terms are strongly orthogonal to each other?
Yeah.
Okay.
Yep. No, it works out very nicely. So, for example, if you want a useful fact, so let's see, what's one corollary? So where Arthur kind of proves strong orthogonality, although he doesn't quite make it explicit, is suppose they take an Eisenstein series coming from a Cuss form, and you want to evaluate the L2 norm of the truncation of that Eisenstein series. Then, because it's a Cuss form, you know exactly what all the constant terms are, and if you apply Brion's trick, you can evaluate by somewhere or another, you can evaluate exactly the kind of integrals you're looking at, and that's what gives you Arthur's formula. So, so the immediate consequence of strong orthogonality is Arthur's formula for it's the Maas-Selberg in higher rank. Okay, I'm through for 5 minutes.
10 minutes, right?
Hmm?
10 minutes, right?
Okay. Whatever you say. Of infinite order. What does an infinite order mean? Well, I take the norm of G equals an algebraic norm. It doesn't depend much. O n. So that's the Schwartz space of an algebraic group, absolutely arbitrary algebraic group. You're all familiar with at least one. If I take R, S of R is equal to S of R. No problem there. But now, let's look at a slightly more interesting case. As I say, it applies to semi-algebraic spaces. Let's look at S of 0 infinity. So S of 0 infinity is the multiplicative group. So in this case, it's all F. It turns out, as you can check as a calculus exercise, it's all F, and so F goes to 0 rapidly at infinity, and F of 0 is equal to 0 of infinite order. Okay. So this is the multiplicative group. This is the real group. Now, the usual Schwartz space defined of the multiplicative group is what you get by taking the Fourier transform, by the exponential. So this is not equal to this space, which is what I like to call Harishchandra's Schwartz of the multiplicative group. And these, to get this space, you replace this by a log G. So if I replace the algebraic norm by a log of the algebraic norm, then that gives me Harish-Chandra space. It's an interesting space, and it's good for various purposes, but in the general world, it's this short spaces which is much, much more interesting. In particular, it occurs in various forms. It occurs in Tate's thesis. So for most number theoretic applications, this is the right short space to use. And Eisenbud and Gravich have all kinds of, I don't know how many papers, maybe 3 or 4, sort of, they keep added to what they knew before. Unfortunately, there's no summary for general use, but it's some of the results are actually very beautiful. Not all. Some are just expected, but some are unexpectedly beautiful. Okay, so I take the short space of G, and now
Of infinite order?
yeah. Taylor series vanishes. So now we know what the short space of G is. Then we have the norm, which I'll sometimes write algebraic norm. And now I want to tell you what the short space of the quotient is. So it's the same thing, only I define with respect to this, and this is equal to the inf of gamma G, of gamma, a member of gamma. And on Ziegel sets, these are essentially the same up to some order of growth. Okay. Now, this doesn't seem like a very deep notion, but it turns out to be a rather convenient notion, and I'll explain it. Actually, I think plays a fundamental role in analysis. So this is what the short space is, and now let's see. So this enables all kind of facts. So let's look at the dual of this. So I call A of G equals the topological dual, continuous dual. So this is S of, this is, again, it's not quite obvious. It's a Frechet nuclear space. The Frechet is obvious. The nuclear is not quite so obvious. And this is a topological dual. So these are distributions. And this notion actually is due to Godema, as far as I know. It was Godema who pointed out that basically automorphic forms are tempered distributions of some kind. That's where the moderate growth condition comes in. See, I always wonder when I was a graduate student why everybody always assumes moderate growth, and the answer is because you're really talking about distributions which are of moderate growth. So that's this, and then this contains AUMG. Well, it contains many spaces, but it contains the space of automorphic forms. And these are the K finite, ZG finite elements. You don't even have to assume they're functions, they're distributions. And so the automorphic forms are just the K finite, ZG finite tempered distributions.
This A is calligraphic.
Huh?
This A is calligraphic.
Yes, it's a calligraphic A, yes. That's, yes. Put a little /cal every time you see it. Yes, that's right. This is my notation. I nothing special about it. Okay, so that kind of puts, for me at least, when I discovered this, it somehow made a little bit of analytical sense for the theory. As I say, I think the notion somewhere, it's a throwaway remark of Godema's, maybe in one of his seminar Bourbaki talks. Okay. Now, so
This H, these are smooth functions, yeah. This
Huh?
H gamma is, because it's mumbled something about distributions, but the A is smooth functions.
the calligraphic A, well, they're automatically smooth.
Yeah.
If it's K finite and ZG finite, that's a finite dimensional space. You can apply convolution operators to it and retrieve it. So convolution operators are all smooth, automatically smooth. So it's sort of, I don't know, it makes, so one of my lifetime goals, which will never be accomplished, is to make the theory of automorphic forms look like the rest of mathematics. It's a hopeless task. It's a purely hopeless, it's just ridiculous thought, but I keep trying. So here's one way in which, to give you an idea of how hopeless the task is, I once met an editor of a very famous journal in analysis at a conference. And we started talking, what did I do? I'm at work in automorphic forms. Oh, you must know Jim Arthur, blah, 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 blah. out of the conversation came the following claim. Under no circumstances is Jim Arthur an analyst. I don't know what he does if it's not analysis. Somehow the guy had some different view of what analysis is or is not. And he was very religious about it. He got really excited. He said, oh, we rejected a paper of Jim Arthur's. Immediately he sent it to us because it's not analysis. So, I don't know. Okay. Hold on for one moment while I page through. Yes, so I want to do some Fourier analysis of some elementary kind. So let's see why these are nice spaces. So let's do some Fourier analysis. So let's look at S of 0 infinity again as a module over the positive reals. Okay. So I take F. Now to make crits unhappy, I will again put a hat on something, but this time it means Fourier transform. I should actually put minus S here, but I'm going to put this, it's the Millen transform. The two schools of thought. Okay. Now, so as a replacement, so S0 infinity contains CC0 infinity. But this is a very nasty space. Because if you look at its Fourier transform, well, first of all, this space here, this embeds into this, and it's closed, and actually in some sense, which I won't explain, the some sense is also another short space. Again, somewhere that's related to more work by Eisenstein and Gravich. So we have a nice exact sequence, and this is closed in this, so you can apply all kinds of nice analytical theorems about this. But if I replace this by CC infinity, this is not a nice short exact sequence. This space is not closed in that, and you don't know, it's kind of messy. It doesn't look good at all. So this is a much more natural space, and that's exactly what Eisenstein and Gravich show you, is that you have all kinds of closure and exact sequences of this kind. Okay. But the next fact is, if I apply the Millen transform to this function, then it becomes very messy. You have growth conditions and infinity as well. You have some sort of exponential decrease, and so on. It becomes very, very messy. You actually have to show that something decreases at infinity, it vanishes at infinity rather than decreases. But this case, the space of all f hat of S equals all f holomorphic in C and rapidly decreasing in the imaginary direction on bounded strips, bounded vertical strips. So these functions rapidly decrease at infinity in the imaginary directions. No problem with, you don't have to move things arbitrarily, you just have to move things arbitrarily far over, and you get a function of rapid decrease when you look at the background. So it's a very nice space, and this is a very nice there. And this actually turns out to be interesting in other ways. Okay. So we can ask for the same thing. We can ask, what kind of analysis do we want to perform on this space? So the question is, can we do Fourier analysis on the short space of G quotient gamma? Okay. And the answer is probably. It's a very interesting question, and it's not in any sense a trivial question, but there are some trivial aspects to it. So the first fact is, so I take P a parabolic in G, and I take phi a member of the short space of gamma intersect P. I can do something similar for other discrete subgroups. And then I define E of phi, or, well, I can also call it E of P of G of phi equals sum over intersect P gamma phi gamma G. And this is, it turns out this is, remember, the short spaces are very nice. This is in the short space of G itself. Not a deep theorem, but not quite trivial either. So this replaces, again, what Langlands does, and everybody else is what at least some other person at this conference has done. Normally you take CC infinity, you talk about pseudo-Eisenstein series and so on. Well, there's no technical reason why looking at the short space is a little better, except somewhere down the line it turns out it is. But anyway, it's the same. And now we define SP of G to be the closure of the image of these in the short space of G quotient gamma. Okay, so to each P, I associate, and I take phi, I'm sorry, for phi cuspidal. So there's a notion of, bye-bye, Joseph. There's a notion of cuspidal on these spaces. Namely, I can do it in stages, but I just didn't want to bother. So I take these, and then I define cuspidal to be those things which are orthogonal to all the images, and then I go back again and do by recursion to define cuspidal for each one of these, and then I take this to be this, so we'll call it P cuspidal. Okay, and then it turns out that this is the direct sum of this over all associate classes, gamma classes of P, of SP cuspidal. Well, I'll just call it SP cuspidal. Okay? So basically, the theorem there's a theorem in analysis which is hidden here, which we've already seen before, actually. First of all, if I have a cusp form, its constant term is 0. All of its constant terms are 0. That means that its truncation is itself. But the function, its truncation is always rapidly decreasing. So if I have a cusp form, it's rapidly decreasing, so that's in the short space. And when you sort of fiddle around with that and talk about maybe some L2 decomposition, that's where you arrive with this. So I have an immediate direct sum decomposition of my whole short space into pieces parametrized by associate classes with respect to gamma of parabolics in G. Okay? And each SP, this is a direct sum of irreducible pieces. Corresponding, well, not irreducible, but what to call it, indecomposable pieces. Direct sum parametrized by irreducible components of gamma, of L2, gamma, and M cuspidal. So in the end, I get a direct sum decomposition of the short space into pieces parametrized by sort of cuspidal components on the different parabolics.
So, should I be surprised that when you talk about cuspidal, you know, the S cusp for a specific parabolic, that's not defined intrinsically using some rapid decay condition on the space, that you have to add this condition of cuspidality?
I'm sorry. So I'm not sure that I understand what you're asking.
Well, for this phi, you wanted to impose this.
So yeah, so let me go back again. I'm short-circuiting. So first of all, I can define, if I take an arbitrary function in the short space here, I can take its Eisenstein series, and that gives me a function in the short space here.
Yeah.
Now, that tells me what the cusp forms on gamma G are. Those are the ones which are orthogonal to every Eisenstein series of this kind. Okay? Now, this applies for any there's nothing special about G. It applies also to all the M's. So I can define a cusp component for each M. And proving by an induction process, I can prove that this sort of statement for each M. So each short space of M decomposes into cuspidal plus other stuff. And the SP here, this space is actually an induced short space in the sense of something. So it becomes a little technical, but that's, when you're all through, somehow I...
So you avoid redundancy by imposing that condition. I mean, you wouldn't have a direct sum. You just have
No, in the end, you really want a direct sum because of the following fact. So the basic problem in this business is to decompose, is to do Fourier transform is to understand each one of these components. So S, P, cuspidal, pi. So I'll give an example of SL2.
When you write equal and direct sum parameterized by something, it's each summoned?
Yeah, you want it, in other words, yeah, you know, in a sense, you know the short space completely if you know what it is. The short space itself is a sum of things, a direct sum. Actually, there's some technical proviso I don't want to get into, but basically that's the way you see it. And so if, in a sense, you understand the short space completely if you understand each one of these. You really understand the computer. We will never do that. We will never understand what the cusp forms are, I think, in any amount of time. But modulo that problem, we can understand what happens. Okay, so what kind of a Fourier transform? So now I ask, what kind of Fourier transform do we have on each SP cusp pi? And so, for example, the trivial one I've already covered. So if I take G equals the real multiplicative group, and I take my gamma equal to plus or minus 1, then you've seen the answer. So the answer in this case, f of s, blah, blah, decreasing in blah, blah, in natural directions. Okay, so that's, in a sense, that's the starting point, but it's good to keep this as a model for what happens in general. Okay. Now, I want to introduce another kind of Fourier analysis, which is not, the face of it, directly related to this. I just want to remind you of a well-known theorem in Fourier analysis. Let's look at a different space. I want you to get a feel. So let's look at L2 of 0 infinity with respect to the additive group. In other words, we apply f goes to the usual and in this case we take lambda greater than 0. So this is equal to f hat of lambda in the usual sense. This is not a smooth function, but it's well defined. And now what we have is my f of lambda is holomorphic in this region. This function is in L2, and its Fourier transform here is on this line is its usual Fourier transform. It's L2, and in some sense, this distribution is the limit of all these distributions. And you can actually specify rather easily exactly what the image of this is. So this is a kind of a, it's not similar to what I said before, but it's an interesting example of a different kind of Fourier analysis. Okay? Yeah, you're shaking your head. What does that mean? Okay, yes. So now I tell you that the theory for automorphic forms is somewhere in between these two. So let's look at SL2. And let's look at the L2, well, of the short space cusp for SL2. So I define E of S equal the sum over gamma intersect P, gamma y to the S plus 1 over 2 of gamma Z, where y is the imaginary part. And then its constant term is equal to this. And it's holomorphic in here, except for a pole here. And it's L2 here, and who knows what happens over here. Okay. So this is a 1-minute summary of the theory of Eisenstein series for SL2. Are there any questions? Ari, do you have a question? No, you're fine. Yes. Okay. So this is what the Eisenstein is now. And now if I take a function in the Schwartz space, I pair it, I define its Fourier Eisenstein transform by the pairing of f modulo E of f when gamma intersect. Well, let's make it H. Okay.
What is written in the diagram?
Here.
Yes.
That's all the poles of the horrible. This is on my pictures from my. You were at my lecture last week? Maybe not. Oh, okay. So you remember I had all these monsters over here. So who knows what the behavior is? You don't care. Okay. So yeah. Okay. So but over here it's very nice. You know that what you do know is with a little bit of work you know that well you have some idea of what the growth of this region is. This is L2 on here. There's a single pole here, and you know what the residue is. It's a constant. So that's nice. So this is a nice function, so f hat of s is nice in the region R of s. It's a negative sign, so it's less than or equal to 2. And you can specify easily some properties. You can characterize it completely. So there are a small number of properties that characterize it. I won't tell you what they are, except that none of them have anything to do with the region, the Eisenstein series to the left of real part equals 0. So the point is that the inverse Fourier transform is very simple. So if I have a function f of s, it goes to the integral 1 over 2 pi I times f of s times E of s d of s, and this is a real part of s equals 0, plus, actually minus, the residue of f of s at s equals minus 1 times constants. So the point is that this characterization, which I'm not telling you precisely, I will probably tell you the next time, it enables this all to make sense. So my function is L2 on the critical line, and that means that I can make sense out of this. In fact, there's a little bit more is true. It actually converges by assumptions on my f. It actually converges absolutely. And then you would expect to somehow pick up something contributed from the constant functions by integrating. It turns out the way to get that is just by the residue. And so I claim this is an inverse Fourier transform. In other words, if
Only S on the critical line in the definition of
hello?
in the transform S is only from the critical line?
Yes, yes, because that's the inverse. So that much of the so basically this is the formula for the inverse L2 Fourier transform, right? I mean, there's nothing special about this. The only thing that's special is that if I assume my f of s has certain properties, this turns out to be also in the Schwartz space. So this formula is the inverse Fourier transform of something in L2, but offhand all I know is that it's in L2. I don't know that it's going to be in the Schwartz space. So the basic theorem is that under certain conditions on f of s, this function will be in the Schwartz space. Okay, now what are the conditions? Well, the first condition is that f of s, so we know that E of s is equal to C of s times E of minus s, and that implies that f of s is equal to C of minus s times f of minus s. And what that means is that if I integrate f of s times E of s, well, let's look again at this. So we want to know that this expression is in the Schwartz space. Okay, now, in general, if I want to know that a function is in the Schwartz space, first of all, that means that it's rapidly decreasing. But under mild conditions on the function, I have to know that its constant term is rapidly decreasing, because I know that the difference between the function and its constant term is rapidly decreasing. So it comes down to knowing that the constant term is rapidly decreasing. You have to verify some mild conditions on F, but that turns out to be easy. Okay.
When you write this term, you mean this?
Hello?
This expression is this expression?
Yes. Yes. Yes.
And if you have more residual spectrum, you?
Just a moment. Yes?
And if you have more residual spectrum,
I'm sorry, who's asking? Ah, yes, way back. Yes, Reznikov.
if you have more residual spectrum,
Yeah, but I don't. It's SL2Z.
yeah, but then
Okay. I mean, there are ways to do this for an arbitrary, nice arithmetic subgroup.
this is a condition which you cannot predict.
That's certainly correct. That's right. No, that's not. Okay. Okay. So we just look at the constant term. So let's see. So we're looking at f of s times, we know what the constant term of this is, 1 plus s over 2 times c of s, times y of 1 minus s over 2 ds, 1 over 2 pi I, plus or minus the residue of f of s times constants. But we know that this satisfies the functional equation, and if I plug this in and just change variables, this just becomes f of s y to the 1 plus s over 2 ds. So this implies this. Okay? But now, let's see, we have an integral here, and we have my residues over here somewhere, and we have my integral here. Well, this is a very simple, the point is we've gotten rid of the C of s, that's the point. So the C of s can cause horrible troubles because I know that C of s has really, it's a nasty, nasty thing over here. So I want to get rid of it. And that's the advantage of looking at the constant term is that automatically you get rid of the problems with C of s. So now all we have to show is that we can move this integral over here and something to do with the residue. Now if we do that, then s is negative. The real part of s is now negative. So if I can move this arbitrarily far over here, this term becomes as rapidly decreasing as you want. So the whole point is to be able to move. Again, it's a contour motion, a little bit different from the one that Optom speaks about. So again, we want to move the contour to the left. Okay, so we have this, we have this. We have my integral here, and we want to move it to the left. Now, it's clear that I've arranged things precisely, so if you can do this, you'll pick up a residue here, and you can just keep on going. So the only problem is to move the contour. And it turns out, well, there are different ways to do that. None of them are quite trivial. In this case, it's relatively easy because we know exactly what C of s is, but you want to somehow not think too hard about that. You want to somehow think of a more general situation. And it turns out that somewhere in the physics literature is exactly the kind of setup that you need to be able to do that. You need to estimate. So what you have is a holomorphic function with certain growth conditions and a limiting L2 distribution of some kind. And there's some arguments in the physics literature which enable you exactly to move that contour to the left. It's very different from the contour motion in Langlands that I mentioned last week because Langlands is much more complicated. And in fact, the contour motion here that I can do seems to contribute something to the results of Opdam, Martino, and Heyermann. Well, that's not quite clear. Okay.
Excuse me?
Hello, I'll be there with you as soon as I erase. Yes?
And so when you move the contour to the left, what if you pick the pose from say s equals to -1? So you'll not have a rapid decay because you will keep the term y to the power 1 there. And I mean even if you move the contour to say a real part -n,
Yep.
you still have the term y to the power -1, say.
No. The star term which I erased had the residue in it. I subtracted the residue. My inverse map had two terms. It had the integral over a real part of s equals 0, and it had a residue. I was subtracting off a residue. It's that, you have that residue term exactly to take care of the residue you get when you move it over to the right.
Oh, you mean the residue coming from the...
Yes,
the
there were two terms in my inverse Fourier transform. Right?
From poles up to the right. It subtracts all poles to the right.
The poles of the
You
Eisenstein
use
series are to the right.
functional equation.
Yeah.
Okay.
And you're left without C of S. You cannot control C of S to the left
Right.
of this line.
Okay, so I'm almost through actually. What I want to do is take you through the sheet here, take you through the literature, and then I'll be through for the day. So next time I'll take up more of this and discuss more about Eisenstein series and higher rank. So, does everybody have the sheet? I think we had one empty one left at the end. We made up 40, there we go, okay. So I've divided these up into topics, but they're not entirely non-overlapping. So the first part is the question of partition. So I mentioned that there are different ways of seeing this partition. As far as I know, nobody has ever written up exactly why Sataki's compactification works. It's an interesting exercise for a graduate course, I would guess. Not very hard. But I think the two interesting papers here, the one of mine and the one of Grayson. Number 3 is my paper, but it's based entirely on, almost entirely on Dan Grayson's paper number 4, which is, he uses what I call semi-stability theory. It is semi-stability theory. So the idea is you have the symmetric space parameterizes certain lattices with certain metric properties. And as I said, what's mysterious about it is exactly how the partition depends on the discriminant of various forms that you get. The only contribution I make is, if you look at number 3, immediately you'll see Dan Grayson had some nice pictures drawn on a Macintosh. I just improved his pictures. That was my... But Dan liked it. He was very happy when I improved his pictures. No competition there. Topic number 2 is truncation. The literature on truncation is extremely sparse. So the original paper is the second paper of Jim Arthur's, number 7 on the list. That's pretty much where all the original arguments go for. There's one very small mistake in there, which I leave you to find. But anyway, this is not too serious. And in fact, pretty much there's one part of the argument in there is not really reproduced well anywhere else at all, I'm afraid. It's really, the literature is very bad. I have a little, very short paper on truncation exercises where I talk about Euclidean truncation and how it relates to Arthur. That's number 8. Truncation theory began with a paper of Langland's in the Boulder Conference. He makes a very short section involving truncation and then passes on. But then the main reference for me, where I learned my truncation theory, was from reference number 10. In, I think, 1983 or 4, Langlands and Lebesgue and a whole bunch of people had a morning seminar on the trace formula. And Langlands and Lebesgue outlined Arthur's theory of truncation in that case. And that's probably the single clearest reference, but it's not so great. This was redone in the book by Lebesgue and Valsverger. But again, and so they improved. The Langlands had a few technical errors. They improved Langland's errors, but I find the morning seminar much more readable. These are all done in terms of Adele groups. Number 12 is in terms of arithmetic groups, which I find, in general, a little more intuitive to work with. But number 12 is not an intuitive paper. It's very badly written. But still, you might want to look at it. The Euclidean subject of truncation is covered in a sheet in Briot and Verne. There's a question. So I have the two different facts about Euclidean truncation. First of all, you had the truncation formula for a convex domain, and then you also had the decomposition associated with the convex domain. And in automorphic forms, you have to go back and forth between the two. The orthogonal decomposition comes from the truncation formula, but it's not easy to see. And the link between these two is something called Langland's combinatorial lemma, a rather obscure lemma, which somehow gives you inverse maps back and forth between the truncation and the partition. And the first place where that was ever explained for arbitrary convex domains is in the last paper by Goreski, Kotwitz, McPherson. There's not much on Schwartz spaces. The most amazing thing about Schwartz spaces is that were invented by Marion Price and Mautner in, 1959, actually a little bit earlier. They gave some lectures on it at the Institute. And they have a Schwartz, the theorem I proved to you is proved by them, more or less the same argument, except that they're doing, well, they're using something very special for arithmetic groups and L functions. It's a remarkable paper, actually. Then I have a few, I've been working on Schwartz spaces for years, and that's what the next 3 papers are all about. I'd like to call your attention to paper number 20. Paper number 20 is a funny exercise. So I've defined what I call the Schwartz space of gamma, H modulo gamma. And then in this paper, I defined something called the extended Schwartz space. And I use this to derive the volume formula for Tamagawa numbers implicitly. And I wouldn't mention this except that if you went to Sakellarides' lecture last week, he refers to that paper, and in fact, he has a very beautiful generalization of my notion of an extended automorphic form and deduces from that. In case you didn't follow Sakellarides, what he's doing there is deducing the trace formula from a form of my Fourier analysis of extended functions. Extremely beautiful idea. I think we'll see more of that. And then the last part, well, I'll talk about next time. I'm through for today.